Chapter 2, Number 1. A charged particle is caused to move between two electrically charged plates, as shown here. A. Why does the path of the charged particle bend? Well, because that's the way charge works. Opposite charges attract, like charges repel. So, B. What is the sign of this electrically charged particle? Since it's bending towards the positive plate and away from the negative plate, the assumption here is that the particle is charged negative. C, as the charge on the plate is increased, what would you expect? Would you expect the bending to increase, decrease, or to stay the same? Well, the way charge works is the more charge you have, the more repulsion or the more attraction you have. So if you charge the plates more, you'd get more of a bend. D, as the mass of the particle increased while the speed of the particle remains the same, would you expect the bending to increase, decrease, or stay the same? All right, so this is what they leverage with the mass of things to figure out whether, to figure out how massive they are. So a heavier particle will be bent less by the field than a lighter particle. So it's just like anything you want to push off its path. If it's light, it's easy to push off its path. If it's heavy and more massive, it's harder to push off its path. So you would decrease the bend in the particle as the mass increases. The following diagram is a representation of 20 atoms of a fictitious element, which we will call nevidium. NV. The red spheres are nevidium 293, and the blue spheres are nevidium 295. Assuming that the sample is assuming that this sample is a statistically representative sample of the element, calculate the percent abundance of each element. Okay, so in order to do this, I count up the number of red ones, I count up the number of blue ones, and I come out with, out of this 20 sphere sample, 8 of them are blue and 12 of them are red. In order to figure out the fraction that each one represents, I multiply it by the total, right? That's what a fraction is, right? The piece divided by the whole. And so what this means is that out of this 20 sphere sample, since 12 of them are red, 60% of them are red, 40% of them are blue, right? I can turn those fractions into percentages by multiplying by 100. All right, B. If the mass of nevidium 293 is 293.15 AMUs, and that of nevidium 295 is 295.15 AMUs, what is the atomic weight of nevidium? So when we have a sample, most of our sample is red, right? It's not equal, right? So this is what's called a weighted average. This sample is weighted towards red spheres. So in order to figure out the weighted average, I multiply the fraction that represents red by its mass, and I multiply the fraction that represents the blue by its mass. And what I get is an average that's skewed toward the red. You know, it's going to weigh more like the red ones because there's more of them. And that's what atomic weight is. It's a weighted average towards whatever fraction of isotope you have the most. Four boxes in the following periodic table are colored. Which of these are metals and which are nonmetals? Which one is an alkaline earth? Which one is a noble gas? All right, so this is how the periodic table, let's look at our periodic table here, that's what that represents. Our periodic table is going to be important in this course. Has a lot to do with how these atoms behave chemically. I mean, that's what this is, right? It's all the atoms that there are in the universe. According to this chart, we have discovered as many as 218 different kinds of atoms. So on this chart, there's an imaginary staircase which divides what we call metals from nonmetals. So if you go to the right side of the chart, as you go further away from the staircase, you become more and more like this thing called a nonmetal. And if you go further to the left, you become more and more like a metal. Until you get all the way over to Group 1A. In Group 1A, these are the most metallic elements, right? You're furthest away from the staircase. So they get a special name. Group 1A elements are called alkaline metals. With the exclusion of that one hydrogen there. I should, put an X in there or something. X that one out. Hydrogen is not part of the Group 1A. We'll talk about why later on. If you're in Group 2A, you're the second most metallic elements, right? So you get a special name. You're called the alkaline earth metals. If we go over to the right side of the chart, this group 7A, gets a special name. These are the most reactive nonmetals, the halogens, and the most nonmetallic elements are the noble gases. Now, all of these gases have the same thing in common. They're very unreactive, and we'll talk about why later on in the course. Notice how we skip that whole pink section in the middle. They get a special name called the transition metals. And again, we'll deal with that, why you're a transition metal later. So as far as our little chart goes here, these are metals, right? They're on this side of the staircase. And if we're looking at the pink one, that fell into column 2A. So, before I do that, right, over on the other side of the staircase, or at the right side of the staircase, these are the nonmetals. If you're looking at column 2A, everything in column 2 represents the alkaline earth metals. If you're looking in column 8A, everything there represents the noble gases. And that's how we look at this chart. Depending on what column you land in, you have a certain reactivity. Does the following drawing represent a neutral atom or an ion? Write its complete chemical symbol, including its mass number, atomic number, net charge, if any. All right, so looking at our atom here, in the little small section in the middle, that's the nucleus. That's where all the mass of the atom is. It tells us we have 16 protons and 16 neutrons. All right, so if you have 16 protons, you are element number 16 on the chart. There's only one element in the universe that has 16 protons in its nucleus, and that is sulfur. This particular sulfur has 16 protons, that identifies it as sulfur, and 16 neutrons. So if I want the mass number, I add up the number of protons and neutrons, and that gives me a mass number of 32. So that's all a mass number is. It's the number of protons and plus the number of neutrons. The number on the subscript there is called the atomic number, and again, that's the number of protons that identifies the elements. Now, since I have 16 protons, 16 positive charges, and 18 electrons, which are negative charges, I have more negatives than positives. So this particle has a net charge of -2. Get into this later on. All right, the chemical formula for the following compound. Is this compound ionic or molecular? Name the compound. All right, so I is a nonmetal, F is a nonmetal. So when you have a compound containing only nonmetals, you fall into this category called a molecular compound. With a molecular compound, the electrons are shared between the atoms. So these fluorines are connected to that iodine. So this thing comes as a unit. It's called a molecule. The way we name molecules is we put the less electronegative element first. Electronegativity is a trend on the periodic table. More electronegative you are, the more you're towards the nonmetal side. The less electronegative you are, you're more toward the metal side. So the less electronegative element goes first in the formula. The more electronegative element goes second. And you put a subscript to indicate how many are connected. So one iodine connected to 5 fluorines. So the way we name this is we just name the less electronegative element, iodine, and then we use a counting prefix to indicate how many fluorines are attached. So the counting prefix for 5 is penta. So the name of this compound is iodine pentafluoride. Notice we don't put a mono with the iodine, right? It's assumed that it's mono if you just have one of them. So iodine pentafluoride, that would be the name of this compound. Hydrogen sulfide is composed of two elements, hydrogen and sulfur. In an experiment, 5 grams of hydrogen sulfide is fully decomposed into its elements. A, if 0.384 grams of hydrogen are obtained in this experiment, how many grams of sulfur must be obtained? All right, according to the law of conservation of mass, the masses have to add up to be the total mass of the compound. So if I subtract the mass of the hydrogen from the total mass of the sample, I get the mass of the missing component, which in this case is the sulfur. B, the fundamental law here is the law of conservation of mass. Dalton is the one who explains why the conservation of mass. Why do we have the law of conservation of mass? According to Dalton, is because this compound is made of these things called atoms, which come in whole chunks only. So we always have the same. So the masses always have to add up because there is always you're never losing atoms during a chemical. The formation of a chemical compound. You're just putting these atoms together to form this new thing. So, law of conservation mass says all the masses have to add up. Dalton said this is because what makes up compounds are atoms, which come as whole units.